Just like do a quick introduction. Hello, everybody. Thanks for coming to the thesis defense today. I'm Greg Gao, thesis advisor. I guess everybody knows Brian is a fifth year graduate student, and today is the thesis defense. So a little bit about the format of the defense. So there will be two parts. The first part is open to public, and everybody can feel free to ask questions, but try to be nice, don't too much pressure. So the second part is so after the first part, can ask the audience kindly leaving the room, and the committee will have the second part. After all this exam, so we'll have a private discussion with Julian about his thesis. And are you ready?
Yes.
All right. Okay.
Okay. Well, good morning, everyone. Thank you all for being here so early in the morning. My name is Julian Deagueros, and today I'm excited to talk to you about my work investigating 2D materials and their applications for field effect transistors, which from now on I will refer to as FETs. Okay, well, to start off, I want to give you a little outline of how this talk is going to be structured. So first, I will present the background and motivation of this work. I will briefly introduce the structure and the operating principles behind our 2D field effect transistors, highlighting the key limitations in the field, and explain how my work tries to address these challenges. Next, I will talk about the fabrication methods used to create these 2D field effect transistors, as well as the measurement techniques employed to characterize their electronic and physical properties. The core of this talk is divided in 3 projects, the first of which I will explore how modulation doping can be used in 2D heterostructures. In the second project, I will investigate how the role of the semiconductor affects certain device parameters, such as the subthreshold swing and the device threshold voltage. And then finally, in my last project, I will introduce a novel method for creating edge contacts for the goal of reducing contact resistance in 2D field effect transistors. And then finally, I will conclude with how the implications of my work can be extended beyond just the specific materials used in this work, and how they can serve as a guide to design and optimize 2D field effect transistors more broadly. And then I will briefly introduce the work that I'm currently working on now and potential future directions. So to start off, why are we here today? Well, for me personally, I'm here today because I want to actively contribute to the kind of research that will indirectly lead to the sort of animation progress that we can see here. So, from over 24 years ago, GTA 3 was released, and we can see the change in the animation from just a couple years ago when GTA 5 came out. Not only that, but there's innovation in the size of devices. So if you remember before, we had this huge TVs the size of fridges. Now we have them the size of small whiteboards. Not only that, but we have also been able to integrate and create smaller devices for medical purposes. So all of these technological advances have been made possible by the increase in the density of transistors on a chip. This follows what is called Moore's law, which is more of an observation than a law, that the size of the transistors will double roughly every 2 years. And we have seen this physically in the form of the shrinkage of the transistor. We can see that there's an obvious trend between the miniaturization of the MOSFET, the metal oxide semiconductor field effect transistor, and the increase in transistors per chip. However, over the recent years, as you can see, this trend has become a bit more stagnant, and that is because as MOSFETs are scaled down, problems due to short channel effects begin to arise. This has led researchers to explore alternative device geometries and or novel materials in an attempt to mitigate these effects. One such material is 2D layered materials. They have attracted particular interest because of their promising physical and electronic properties. The most common 2D material that we know is graphene. So graphite, what our pencils are made of. Because each carbon atom in this graphene is bonded together by weak van der Waals forces, we can easily use the tape to peel apart a single layer of these materials. So we can form atomically thin flakes from these materials that do not have dangling bonds similar to, or unlike their 3D bulk counterparts. And this allows them to become immune to these short channel effects. Additionally, the smooth interface allows them to be assembled into atomically sharp heterostructures. And their versatile electronic properties allows them to be used in a wide variety of applications, ranging from electronic to optoelectronic to energy storage. And perhaps the most exciting part of this is that, as I mentioned, you can use a simple piece of tape to isolate these layers and assemble them in any configuration that you can think of. But before I dive into 2D field effect transistors, I want to make sure that we're all on the same page about how they're structured and how they work. So starting from the bottom up, we have the substrate, which consists of a metal gate and an oxide dielectric. This is typically an insulating material. After this, we have our semiconducting body. And then finally, we have our metal contacts that make our source and our drain. Note that this is not drawn to scale, because if it was, I would have no room for anything but the oxide. So the metal gate and the oxide layer is around 1 millimeter thick, whereas the semiconducting body is 1 nanometer thick. So you can guess the orders of magnitude is very different. That's why I put it in this non-to-scale image. But you can also tell that this is very similar to the MOSFET configuration, where we have a metal gate, oxide dielectric, semiconducting body. The difference is here that the channel can be made to be sub 1 nanometer in thickness, whereas with typical MOSFET devices, getting anything below 5 nanometer in the channel thickness leads to a degradation in the device mobility and thus its performance. Again, similar to the MOSFET, the 2D FET is a voltage-controlled current source, meaning that you can apply a gate voltage to tune the conductivity between the source and the drain. This device operates in 2 modes, an on mode or an off mode, which is determined by whether or not there is a presence of a conducting channel in between the source and the drain. This can either be with holes or with electrons. So in theory, we can change the polarity of the, we can control the carrier type in our channel by changing the polarity of our gate voltage. So similar to a parallel plate capacitor, where if you apply a negative voltage on one terminal, that will induce an electric field that will attract positive terminals on the other side. We can use this to either attract holes or electrons into our channel simply by changing the polarity of the gate voltage. And this is what gives the on state. The off state just simply is the lack of any channel, any conductive channel present. Oh, sorry. Okay, so now that we've covered how 2D field effect transistors work at the fundamental level, we can shift as to what is happening in the current state of the art. So many studies have reported high performance 2D field effect transistors. For example, looking at the figure here, we see that the mobility, which is a key device parameter in field effect transistors, these devices made from 2D field effect transistors have the ability to surpass the benchmark mobility set by the International Roadmap for Devices and Systems. However, as you can see here, most of these are focused on a couple materials, and they're also focused on monolayer or few layer flakes. Despite the fact that, as you can see from this figure here, if you look at a 10 nanometer black phosphorus field effect transistor compared to a 2 nanometer one, you would have a higher mobility. So this has kind of prompted the interest in discovering multi-layer flakes and how thickness plays a role in device parameters. And so this gap in the understanding is further complicated by the fact that a lot of the engineering strategies tried to optimize the performance of these 2D field effect transistors is based off silicon technology. Despite the fact that there are key structural differences. So for example, in a MOSFET, you have contacts that are made by ion implantation, whereas in our 2D field effect transistor, this is done by directly adding or depositing metal on top of our substrate. So that's going to change the transport properties of the device. The other difference is the way that the oxide is, or the dielectric layer is incorporated. So in typical MOSFET devices, you can use thermal oxidation to produce a silicon oxide, whereas in 2D materials, because they have inert bonds, you can't really use that to your advantage to create a oxide layer for it. As a result, it is crucial to experimentally validate whether these traditional engineering techniques are actually effective when applied to 2D systems. So to address these challenges and better understand what truly governs 2D field effect performance, my work will focus on one central research question, which is what material properties and device geometry determine the device parameters of 2D field effect transistors. To explore this, I will walk you through 3 of my projects, each of which targets a different aspect of device design. So in my first project, I will explore how heterostructures, contact area, and material thickness determine things like device hysteresis, carrier density, on current. In my second project, I will talk about how contact metal, material thickness, and dielectric thickness determine device parameters such as the subthreshold swing, threshold voltage, and semiconductor capacitance. And finally, in my last project, I will explore how the contact geometry, either edge contact or all-around contact, affects things like the contact resistance, the on current, and the carrier density. Okay, but before I dive into how my projects contribute, a tiny break into the growing foundation of the knowledge of 2D layered materials, I would first like to walk you through the fabrication methods and measurement techniques used in this work. These methods are going to be essential for the building, probing, and understanding of the devices that I will be presenting to you today. So to start off, to isolate our layers, the first thing that we do is called mechanical exfoliation. So this involves dabbing a bulk piece of crystal onto a tape because, again, they're held together by weak van der Waals forces. By folding the tape and peeling it apart, we can peel apart these individual layers. Then we place our substrate consisting of the metal gauge and the oxide over this tape, heat it up at a specific temperature for a specific time on a hot plate, release it, and then slowly peel it off to ensure that the flakes don't crack when you peel apart the tape. Once we have our flakes on our substrate, we need to create regions that will eventually become the source and the drain contacts. We do this either by using the shadow masking method, in where we use the copper grid to create regions of empty space where metal is to be subsequently deposited. The other method we could use is photolithography, similar to the shadow masking method. Instead of a copper grid, we use the polymer, also known as a photoresist, to define the pattern, the regions that we want to open up for the metal to be deposited in. Once we have that, we can go ahead and do our metal deposition. So the two most common methods used in this work are electron beam evaporation and thermal evaporation. So in electron beam evaporation, you have an electron beam, you point it at your source that will heat up your source. The evaporated material will then scatter back and deposit itself onto your material or your substrate. In thermal evaporation, instead of using an electron beam, you simply use a current passing through a metal boat containing the source material that you want. This current will heat up the source material, and then eventually that will, because this is in vacuum, rise up and deposit itself onto your substrate. After this, we finally have our device as pictured here. And we can go ahead and set up for electronic measurements. So using a probe station, we can probe the transfer properties of our device by taking current voltage measurements to generate two types of graphs. The first one being output curves, in where we're looking at how the source drain current changes as a function of the source drain voltage. And then we can also extract transfer curves, in where we look at how the source drain current changes as a function of the gate voltage for a fixed source drain voltage. So for our first measurements, or output measurements, we can actually get contact information from the type of behavior that they exhibit. If they exhibit a linear behavior, we can call it an ohmic contact. If they display a nonlinear, almost exponential behavior, we call that a Schottky contact. We can approximate whether or not they would be ohmic or Schottky, depending on the difference between the work function of the metal chosen and the Fermi level of the, material that we're looking at. So contact behaviors from output curves, and we can get a sense of how our device responds to the application of a gate voltage by looking at the transfer curves. So again, this curve, this measurement looks at how the source drain voltage changes as a function of the gate voltage. From these kinds of curves, we can extrapolate important device parameters such as the threshold voltage. To do this, we simply look at the linear regime of our graphs, we draw a line and see where that intersects the zero axis. And then that will give us our threshold voltage. This is a measure of how much gate voltage is needed to turn the device on. The other device parameter that we can extrapolate is the mobility. So how easily can carriers move along the channel for either holes or electrons. So this again is done by looking at the linear regime where the device is on, taking this slope and along with other device geometries like the channel length, channel width, oxide capacitance, and source drain voltage, inputting that, we can obtain a value for the mobility. Finally, another important key parameter that we can obtain from this graph is the carrier density. So how many carriers are participating in conduction in the on state? So we can do this by simply drawing a line across what gate voltage we want to look at. So in this case, I've drawn it for 20 volts and minus 50 volts. They have to be above the threshold voltage, of course, because we're looking at the on state. And simply by looking at the equation of the charge for a parallel plate capacitor, we can obtain the charge density for holes and electrons by plugging in this value, the threshold voltage, the oxide capacitance, and then we'll get a value for the carrier density. We can also obtain values of device parameters in its off state by looking at the semi-log plot of this graph. So one of the device parameters that we can obtain is the subthreshold swing, which is how much gate voltage is needed to induce a decade change in the current. This is kind of a measure of how good your device is at switching. So ideally, you would want this to be very small. You don't want to have to apply a large gate voltage to turn your device on. The way this is calculated is looking at the smallest on current or smallest off current and the onset of thresholds current. So if you recall from the previous graph, the threshold voltage for this device was around -5 and -45. So that's where I drew this line. So by simply looking at the inverse of the slope of this line, we can get a gauge for the subthreshold swing. In this case, these are not very good at turning on. So the subthreshold swing here is in volts per decade. Ideally, we would want this to be in millivolts per decade. And we will explore why this is the case for our devices in the second project. The other key device parameter that we can obtain from this graph is the on-off ratio, which tells us how many orders of magnitude in the current the gate voltage can change. Ideally, again, we would want this to be very large. However, in this case, by looking at the minimum off current and maximum on current, we see that it's just the value of 10 to the power of 3. And now that we're done with the electronic characteristics and how to obtain device parameters from the transfer curves, we can look at the different ways in which we characterize their structural properties. One way we do it is using Raman spectroscopy. So in this method, you shine a light, the light will be absorbed by the molecules in your system. The outcoming light will give you information about the vibrational modes in the crystal. We use this for a couple of different reasons. So our 2D materials come in many different polytypes. The polytypes are not easy to identify based on optical images, which is why it's important to use alternative methods to characterize their structure. So by looking at the distinct modes of each polytype, we are able to identify one polytype from another. The other form of material characterization that we use in my work is atomic force microscopy. This involves the use of a vibrating tip rastering across the surface to map out its topology. We use this to obtain high profiles of our materials, as it is not easy to determine their thicknesses based on optical images. Okay, and so now that we are done with the foundation of the fabrication and characterization techniques, we can move on into the my first project, where I explore the application of 2D heterostructures and field effect transistors. So this project began as an attempt to increase the mobility in group 3 semiconductor indium selenide. Indium selenide is a promising material for high-speed applications because of its high room temperature mobility. However, it is very sensitive to the semiconductor dielectric interface. As you can see here, depending on what is underneath the indium selenide, whether that is silicon oxide, surface modified silicon oxide, a polymer PMMA, or silicon nitride, that will change not only the mobility, like we said, the slope of this nonlinear regime, it will also change the device stability. So this change in the threshold voltage is what we call hysteresis, and it's not really something that we want to see. This problem is not new to 2D materials. It's common in 3D devices as well. And in 3D devices, the common methods used to try to overcome these are implementing high K dielectrics. This is used to alleviate the Coulomb scattering due to traps between the semiconductor and the dielectric interface. The other method is using heterostructures, in where you use two materials of dissimilar band gaps to be joined together and form a potential whale where you can trap electrons of really high mobility. These are known as high electron mobility transistors, also known as HEMTs. And we will actually be borrowing this idea from 3D devices and implementing that into our 2D materials. So to see if we can create a 2D HEMT, we have to look at the electronic requirements and the physical requirements needed. The electronic requirements include a difference in the Fermi level. We need this to introduce doping. We also need a conduction band offset between the two semiconductors used. This is needed to form the triangular potential at the interface that will trap the electrons. Additionally, we need physical requirements, so a small lattice mismatch. The reason why HEMTs are so good at having high mobilities is that there is very, very little mismatch between the two materials used. If we look at the band or electronic properties of indium selenide and gallium sulfide as presented on the right, we see that they do have a difference in the Fermi level, meaning that we can, in theory, dope the indium selenide by placing the gallium sulfide on top. Additionally, they do possess a conduction band offset. So in theory, there should be the formation of a triangular potential at the interface. Finally, even though they don't have exactly similar lattice constants, they do have a similar lattice structure. And so ideally, we will see whether or not that plays a role in whether or not we can make these 2D HEMTs.
Question.
Yes.
You have quite a range of band gaps with all these materials here. What is the origin of that?
Quantum confinement effects. So this is thickness dependence. Yes. So this range is for as you go from bulk to monolayer. So for bulk values, you have typically smaller band gap values. But as you go to the monolayer form, quantum confinement effects increase this value. So before I go on to talk about these 2D HEMTs, there's quite a few different device geometries that I'm going to introduce because I want to look at a couple of different things. So as I mentioned earlier, I suspect that the gallium sulfide is going to introduce some electrons into the indium selenide as soon as I put it on top. So in order to check whether or not that is correct, I am going to use a pre-made indium selenide transistor and simply directly stack a gallium sulfide material on top. And I will measure the device properties before and after the stacking to see what the results are. Then I will go on to look at what happens if I put the gallium sulfide underneath, as we want to use this as either dielectric or a substrate material. So it is important to look at what the device would behave if it was placed underneath the indium selenide. However, I will explore two different contact geometries, one in where the contacts are only touching the indium selenide, so that would be device type 1, and another contact configuration where the metal is touching both the gallium sulfide and the indium selenide, referred to now as device type 2. So for the first type of device where I have a pre-made indium selenide device and I stack a piece of gallium sulfide on top, I obtain the transfer curves displayed in the figure here. So as we can see, the threshold voltage for indium selenide by itself is around 20 volts, whereas that for the heterostructure has been reduced by minus 15 volts to around 5 volts. So this is indicative of the charge transfer. If you remember, we can obtain the amount of carriers participating in the conduction at any given gate voltage. So if we look at 30 volts, for example, the number of carriers participating in conduction is much larger in the heterostructure than in the indium selenide, suggesting charge transfer from the gallium sulfide into the indium selenide layer. Then we explore what happens when you apply.
When you say charge transfer, so what kind of charge? Electrons or holes?
Electrons.
So why electrons?
Because
just like based on the curve.
So based on the curve, we expect it to be. Okay, electrons, because it means it takes less gate voltage to turn it on, meaning that there is a higher presence of electrons already. Whereas if we had expected these to be holes, we would expect this shift to go to the right. Because it means if there's more holes, it means you need to apply a greater gate voltage to actually induce the electrons. But if the electrons are already there, you don't need a higher gate voltage to introduce them into the channel.
As long as we're asking questions on this one, so you can assume that no current flows through the gallium sulfide.
Yes. Oh, why we can assume that? That's a good point. Well, we're assuming that most of the conduction happens in this region between the source and the drain. And so whatever is happening, the biasing that is happening in the gallium sulfide will only really be along these, along the sites where the gallium sulfide is touching the indium selenide. And I've actually created different devices in where it is not touching the metal pads, where it's exclusively in the channel, and we still see this effect. So that's what led me to believe that it's not the conduction in between the gallium sulfide that is causing this.
And we also measured, right, just the gallium sulfide device alone.
Yes, yes,
So
and
what's
so
that
it's very
mean?
resistive. So it's the current is in the orders of 10 to the -4 microamps. So that is what, like tenths of picoamps. So very low. So that's what led me to believe that there's no current flow through the gallium sulfide yet. Okay, so going forward, we can explore the other two different device configurations, and we notice two distinct behaviors. So for device type 1, we experience a larger current density and a reduction in the hysteresis, whereas in device type 2, we see a larger hysteresis and a decrease in the current density. This trend is observed across multiple devices, so it's not that we're just seeing a couple and leading to these conclusions. So what we decide to do is conduct time-dependent conductance measurements to see where it is that this current is flowing in each device type. So in device type 1, we look at the transfer curves and the time conductance measurements as we change the gate voltage from 0 to 20, 20 to 40 volts, 40 volts to 60. And we see that there is a significant by exponential decay in the current for the devices in the device type 1 configuration in the order of a couple seconds. So if you recall from maybe physics 2, when we were introduced to RC circuits, we can actually model this as an RC circuit in which each layer that the metal contact is touching results in an additional resistor in the circuit. So as Professor Berzofsky asked previously, how do I know that there's no current flowing through this device? Well, I did the measurements. I know that the resistivity of gallium sulfide is in the order of gigaohms, whereas that of the indium selenide is in the megaohms. So that change in the resistivity will induce another parallel plate capacitor that will increase the what is it called? Relaxation time. So relaxation time tau is related to the resistivity and the capacitance of the capacitor in the circuit. When we have the metal touching both of the pads, the R is no longer just the resistivity of the indium selenide, but also the resistivity of the gallium sulfide. So that will increase the charging and discharging time, hence the bi-exponential decay that we see in the order of a couple seconds in the time conductance measurements. Apart from that, in the devices that we do see the decrease in the hysteresis and an increase in the on current, when we go ahead and do low temperature measurements, we see that they have a higher current density than the field effect transistors made from just bare indium selenide. However, this is only really the case for heterostructures and where the indium selenide is thin. This is again pointing towards the need to evaluate the role of thickness on the device behaviors of our 2D FETs. Another thing that points towards the importance of the role of thickness in our device parameters is looking at the mobility as a function of temperature for a series of different heterostructures as well as bare indium selenide flakes. So for example, we see here that the curve with the diamond in black is a thin indium selenide flakes. At temperatures below 180 degrees Kelvin, we see the presence of impurity scattering. So this is seen as a power law dependence, positive power law dependence. Whereas for thicker indium selenide, this is absent. However, in our heterostructures, we see that it's similar to what we would see for thick indium selenide. So essentially, we are able to decrease the impurity scattering and the heterostructures within indium selenide by introducing the gallium sulfide to the system. So in summary, we have presented 3 different device configurations, and we have explored how the hysteresis and the current density is affected by the contact configuration. We have noted that direct contact with the gallium sulfide will lead to current induction that will take away current from the indium selenide, thereby reducing the maximum on current and inducing hysteresis. So we believe, right, so we see that there is, again, this dependence on the thickness of the material. And that kind of prompted me to explore the next topic, which is the role of the semiconductor thickness on device performance. So one key device parameter that we will be exploring is the subthreshold swing. So the subthreshold swing is a measure of the efficiency of the device to switch on between on and off. So this is a graphical interpretation of what ideally a graph would look like. So our actual graph looks like the one in blue. Ideally, this switch would be a 0. What would it be? A delta function? No. Ideally, we would have no current in the off state, and then we would simply apply a gate voltage, turn it on, and then we would have some finite current in the on state. But in actuality, that is not the case because we always have some kind of carriers due to thermal excitation. So there's always going to be some finite current. Ideally, we want this current to be as small as possible to lead to a smaller standby power. So experimentally, this can be calculated from the transfer curves, like I explained in the method section. However, experimentally or theoretically, it is dependent on the semiconductor capacitance and the oxide capacitance. So a lot of efforts have been made on trying to increase the oxide capacitance such that the depletion capacitance is negligible. However, as you can see here, the depletion capacitance is calculated using typical MOSFET equations that require knowledge about the carrier density and the built-in potential between our semiconductor and our metal, which with 2D materials, because they are they have thickness dependent properties, this varies from material or from device to device. And in order to obtain value for the carrier density, we would have to do Hall measurements, which would be very time consuming. And we would have to do that for every thickness, which is not easy to do. So in order to kind of bypass this, I decided to look at the relationship between the depletion width and the carrier density. So the carrier density in 3D is, of course, in centimeters per or electrons per centimeters cubed. But if you recall from my method section, the carrier density that I gave you was in centimeters or in electrons per centimeter squared. So in order to go from centimeter squared to our 3D carrier density, all we have to do is divide by the thickness of our semiconductor. So in tungsten diselenide, the typical carrier densities are around 10 to the 10 electrons per centimeter squared. The average thickness of our devices used in this project is around 20 nanometers. So that gives us a carrier density of around 10 to the 16. If we look at this graph here of the width as a function of impurity concentration for silicon devices, we see that for this carrier density with no gate voltage applied, the depletion width is above 100 nanometers. Recall that I stated that the thickness of our devices was 20 nanometers. That is much larger than the thickness of our device. So because of this, I decided to simply take the depletion capacitance to be the thickness of my flake. So that is the big approximation that I am making. And I can actually use that to explain the differences in the device variation with thickness. So one of the things that we notice is that for thinner flakes, we see a increase in the threshold voltage from the left to the right. We also see an increase in the subthreshold swing for thicker flakes. And we can actually explain this by just simply looking at our device and considering it as a equivalent circuit in where the semiconducting body and the oxide body are forming two capacitors connected in series. Because they are in series, the capacitors share the same charge. So the voltage drop across the semiconductor and the oxide has to be equal to the voltage drop applied by the gate. So again, if we look at what the capacitance value is for a parallel plate capacitor, it is proportional to its dielectric constant and inversely proportional to its thickness. So for thinner flakes, meaning this thickness is very small, you have a higher depletion capacitance. This higher depletion capacitance, so if you recall, for any given parallel plate capacitor configuration, if you have a larger capacitance, the potential drop across it will be small, right? So because our capacitance or the semiconductor capacitors for thinner devices is much larger than that of the oxide capacitance, we will experience a much larger potential drop across the thinner flakes, meaning that we need to apply a higher gate voltage in order to see them turn on. Hence why we have a increase in the threshold voltage for thin devices and a decrease in the threshold voltage for thin devices. So in order to verify whether or not this approximation of taking the semiconductor thickness to be the semiconductor depletion width, we extrapolate the semiconductor, or we extrapolate the subthreshold swing of our devices and compare it to the calculated subthreshold swing using the equation that I presented earlier. So once we do that, the points, the circles that are either filled or unfilled represent the extrapolated values, whereas the calculated fit is the one with the dashed lines. We see that the calculated subthreshold swing does not align well with our fit, and that is because we underestimated and neglected to include the interfacial trap capacitance. So physically, this arises from the fact that the oxides that we use are not made perfectly. They have some kinds of impurities inside of them that will introduce traps. These kinds of impurities are either positive or negative, and their ultimate sum will result in this interfacial trap capacitance. If we add this additional parameter to our fit, we can extrapolate values for the interfacial trap capacitance, which align with the other range of values that we see of tungsten diselenide on oxide dielectrics. So to further verify our use of the semiconductor thickness as the semiconductor depletion width, we are going to try to calculate the band gap value from our bipolar transfer curves. So like I mentioned before, the potential drop across our device can tell us about its band gap value simply by looking at where the onset of threshold is. So at the onset of threshold, this means that we have moved and modulated the Fermi level to either be at the top of the conduction band, or the bottom of the valence band, or top of the valence band, bottom of the conduction band. And so by simply taking the difference between these threshold voltages and taking into account the geometric configuration of the thickness and of the semiconductor and the oxide, we can find a value for our for the band gap of our tungsten diselenide flakes. So simply by plotting this shift in the threshold voltage as a function of this depletion capacitance and oxide capacitance, we can obtain a value for the band gap, which is approximately 0.9 EV, which is similar to the band gap values obtained experimentally in tungsten diselenide devices.
I have a question. Why is there a scatter in the measurements? Are those different devices? different
Yes.
Measurements?
Yes, so these are different devices. Yes, so for each,
Okay, yeah, that's.
yeah, so each
Yeah.
point is one value of this threshold voltage. So this was done for a series of devices with not only different thicknesses, but different offset thicknesses as well. Okay, so in conclusion, we realized that we can model our 2G field effect transistor as a capacitive voltage divider. This can help us explain the reduction in subthreshold swing and negative capacitance 2G field effect transistors. We can also use this method to extract band gap values from bipolar transfer curves. This removes the requirement of using a highly capacitive dielectric, which is not always easily accessible. And so now that we are, we're going to come full circle and go back to the role of metal contacts on device performance. Similar to how we talked about the role of metals in our 2D heterostructures. So as you might have already gathered, contacts play an important role in device performance. They are the primary mode of carrier injection into our material. They also provide an additional engineering parameter, so we can choose to selectively or preferentially conduct holes or electrons depending on the type of metal that we use. However, this is just in theory. In actuality, these deposition processes induce defects into our materials, which can introduce levels, trap levels within the band gap that can not allow us to tune the Fermi level as freely as we wish. One method that scientists have tried to use to overcome this limitation is incorporating the use of edge contacts. So in this case, the contact is done selectively to be on the sides of our 2D flake instead of on top and on the sides. However, there are difficulties creating these 2D contacts. The most common methods are using plasma etching and metallization, as well as phase engineering. The issues with this is that etching is not suitable for all 2D materials. Some 2D materials are more sensitive to it than others, so it's not a method that can be used for all materials. The other method, phase engineering, is also not applicable to all materials, as not all materials have a semi-metallic or metallic phase that they can be converted into. And as I mentioned, our current deposition methods are shown to induce structural defects that can negatively affect the device performances of our transistors. So this is caused the need for a low energy metal deposition method. So what we decided to do was borrow some techniques used in electrochemistry using copper plating. So the main principle behind electrochemical deposition is you have a battery or some sort of way to control the potential between your cathode and your anode. You drive electrons towards the material where you want your metal to form. The solution will have ions of the metal that you want to deposit. The ions in the solution will be attracted to the metals on the cathode that you want. Once they meet there, they will recombine and form the metal material that you want. However, you might notice that in order to do this, you need to have a metallic sample, both for the metal that you want and where you want your metal to be deposited. But as if you recall from my device structure, our devices are on top of an oxide layer, which is a very insulating layer. So in order to be able to do this process, we need to ensure that we have a conducting surface. So in order to do that, I created a mask so that I could have an array of transistors that I could easily cleave in the middle. So along here and here, to then separate after the electroplating, so I can go ahead and do electronic measurements. So MOS2 flakes are exfoliated and using a stamp placed over on top of these pre-made patterns in where the copper is expected to deposit on these sides. So doing that, we can actually go and perform our electrochemical deposition. So we can perform this in a 0.1 molar of copper sulfate solution. This was done at a current density of 1.5 milliamps per centimeters. Sorry for that. For 60 seconds. The potential of the working electrode is monitored using a potential stat. After the deposition takes place, we go ahead and take optical and SEM images. And we confirm the conformal deposition of copper along the sides of our MOS2 flakes. So you can see here, this is the MOS2 flake, and this is the copper deposited on the sides of it. However, from the SEM image, you can see that there's high surface roughness, which is problematic. Imagine going down Little Italy really fast. It's not going to be fun. So that's exactly what these electrons are going through when they're traveling through this. So the next steps that we're trying to incorporate is, oh, sorry.
Can you go back one slide, just to the first, there you go. So, no, forward. So copper grains, how do you, can you point to me how you know these are on the side and not on the top of your two-dimensional material?
Because I did this other measurement where I did it tilted. And when you see it tilted, you see that it's kind of sandwiched in between, as opposed to grown directly on top. So I can show you more tilted images.
Maybe during the
Okay,
longer
yeah.
discussion. Then.
But that's how I was able to confirm that it was through the edges and not directly on top. And the other way I can tell is that, so in this case, so this was before I did the mask. And in this case, I simply used the common method of depositing metal and where I used the shadow mask. And so you can see here that this is the flake with metal on top of it that I deposited with e-beam evaporation. So you see that the copper only grew on the flake where the flake had metal, not on the side where the flake didn't have any metal. So that's another way I can tell that it is only depositing itself on the metal sides and not on the flake itself. So, right, because of the roughness, we want to explore other methods of doing this deposition, particularly electrochemical atomic layer deposition, in where you specifically use a sacrificial zinc layer to replace the copper in cycles. And this will ideally result in a monolayer growth of the copper on the edges of the MOS2 flake. So we have wrapped up. Thank you. Thank you. No, not yet. We have the conclusions. Spoiler alert. So in conclusion, to wrap all of this up and again, answer the main question of, how do device parameters affect device, how do material parameters affect device parameters? So in my first project, modulation doping, in indium selenide gallium sulfide heterostructures, we saw that by selecting the materials with the right difference in Fermi levels, we can use these heterostructures to modulate the carrier density and the on current of few layered semiconductors. We saw that we can decrease this hysteresis by selectively contacting material of interest or by reducing the trap density in the second material. The results in this work prompts further investigation on experimental bandgap values. So the bandgap values that I showed were done experimentally, but only for a couple, few layered materials. So it's interesting. Well, it would be interesting to see how this goes on for multi-layer flakes beyond, say, 20 nanometers. Like, where is it that transition where you go from bulk properties to non-bulk properties? Again, further investigation is needed on the effect of contact area. So I talked about contacting the metal, this material specifically, but what about the area? Like, if I contacted more of it or less of it, would it be more or less impactful? And then finally, there needs to be other methods of reliably obtaining monolayer indium selenide or indium selenide of a particular thickness. So this can either be done by implementing chemical vapor deposition growths of the material or simply finding better ways to mechanically exfoliate and get higher yield. For my second project, where I looked at the role of the semiconductor and oxide thickness on the behavior of 2D field effect transistors, we saw that the semiconductor thickness determines the semiconductor capacitance, which then determines the threshold voltage and the subthreshold swing. We can manipulate the semiconductor and oxide thicknesses to give us different values of threshold voltage and subthreshold swing. So for example, there's two main different modes for MOSFETs. We have the depletion mode, in where you typically need to apply a gate voltage to turn the device off. And then we have enhancement mode, in where the device is typically off and you need to apply a gate voltage to turn it on. So simply by changing the thicknesses of our materials, we can change from either going into a depletion mode, FET, or an enhancement mode, FET. However, further investigation is still needed on the thickness dependent properties of the dielectric constant. So in this, we assume that dielectric constant was constant for all thicknesses. That is most likely not the case. Additionally, we should also explore nonlinearities in the subthreshold regime. So, why is it that it's not such a sharp line and there's some curvature that is there? And then for my electrochemical deposition of copper edge contacts, further investigation is needed on electronic measurements, comparing the contact resistance of the devices obtained here versus what we get for the contact resistance of our devices used fabricated in our typical methods. We also have to look into whether or not this process intercalates copper atoms into our material. There has been some literature that says that copper is too large to intercalate itself into MOS2, but it has been used for doping in tungsten diselenide materials. So it might be interesting to change the material that we're using and see if we can also introduce doping apart from creating edge contacts. Additionally, AFM measurements are needed to characterize the surface roughness and to get a more quantitative value of what this is. Future work includes looking at heterostructures again, but in this case, looking at whether or not I can use another anisotropic heterostructure to induce that same electronic and anisotropy in my original device. And so here we can see that we've taken the transfer curves of an indium selenide device capped with an MO3 layer, and we've looked at the transfer curves going in one direction as opposed to the other. We see that there is a distinction in the threshold voltage of one of these sides, not the other. Also, the maximum on current. So this is the potential avenue that I'm looking to explore. And with that, I would like to thank everyone for being here. Expanding Horizon initiative that allowed me to work without having to TA for the past 4 years. My committee, thank you all for being here. My colleagues that have helped me with these projects, faculty and staff, family and friends. Yeah, and without further ado, I will take questions.
Congratulations on finishing half of the. Before we start the second part, that's the audience, yeah.
First, thank you for acknowledging the administrative staff. They do quite a bit of work to keep things running around here.
Yeah, it says many more, but I didn't have enough room.
No,
I'm
but
sorry.
I saw like Georgia and Jackie and Valerie, et cetera. But the question that you talk about all these effects with the thickness, does the length or the width have any impact, and how do you account for that?
Yes, so you might have noticed that my curves are all in current densities. So for example, here, so this is divided by the width of the channel. That is done to make sure that we're not unevenly, comparing one device over the other.
Okay.
And then in terms of the channel length, all our devices have approximately the same channel length because we employ the same copper grids. So they will all result in around 15 microns. So that's relatively constant. So that's why I didn't really talk about the effects of that on the device performance.
Okay, great, thanks.
Well, you go to slide 30. Yes, 30. Yeah. And so you talked a little bit about the time dependent measurements and how you get your different curves. Could you elaborate a little bit more on how that affects the hysteresis?
Yes, so the decay in the current is telling us, there's current going somewhere else. So current going into the gallium sulfide is what we believe is causing this hysteresis. So ideally, the gallium sulfide would be an insulating material that no current could flow through it. But because there are presence of traps, whether or defects, either introduced during the growth process, or since this device is very air sensitive due to the oxidation from the oxygen in the air or the humidity, these can all introduce traps into the gallium sulfide layer. So these traps will be activated once current is flowing through here, right? So this shift in the threshold voltage is occurs because the material underneath thinks that it's looking at a different voltage than it think it is. So for example, here you would expect this to be on at 40 volts, but instead it turns on around minus 20 volts. This is because there are traps inside the gallium sulfide layer that are making the surface around here appear more positive than it actually is. So instead of actually it's being minus 20 volts, the indium selenide thinks that it is in a landscape and where it's actually 40 volts. And so that's why you see this shift in the hysteresis. The shift in the hysteresis is also related to the voltage range that you apply, right? So depending on the range that you apply, that will determine how many traps are inside. So if you go to a higher voltage range, you'll increase the number of traps in here. Hence, you will have a larger width of this hysteresis. Whereas if you limit it to, say, plus or minus 20 volts, you do not see this. Does that answer your question?
Can I ask a question, even though it's under our time, but it's on the same topic.
Mhm.
How long does it take to do those hysteresis loops? In other words, how does the time scale there compare to the time scale for the curve on the right?
So this is taken in seconds, but each data point is done 20 milliseconds. So here the rate at which I'm sweeping is done so that it is the same rate as this. So this I'm sweeping at, I want to say 1 volt at per 0.2 seconds. And so I tried to make sure that this was also in the same time scale as that.
So the whole loop takes.
So the whole loops take, okay, so if we do 0.2 seconds for 1 volt, we have going 60, 120 times 2 to 40 times 0.2, so about 20 seconds, 12 seconds. So the whole thing would take about 12 seconds.
And if you do it at a different rate, would you see a different hysteresis?
Yes, yes. And that is because the relaxation times of these traps is different. So depending on the rate of these traps, that will affect the hysteresis. And if you scan at a rate much higher than these traps, then you might bypass it all and just not see any hysteresis. If you go too slow, you might see them more obviously. And so the width of it will decrease, the current density will also decrease. Or sorry, the width of the hysteresis will increase, the current density will decrease.
So if I follow up with that, okay, so you observe hysteresis is, it's some kind of thing you don't like, right?
Mhm.
But you did this experiment pretty slowly, right? Like a few seconds. But our transistors operate like a gigahertz. Does that mean that this will not be an issue if you use it in like a CPU and operate it at a very high speed? Or do you believe that?
It can be if there are no traps that are released in that time scale. But it would be interesting to see, yeah, if we could do that. Yeah, I think it might be possible because I've definitely done the measurements with like waiting no time, and it's did lead in a reduction in the hysteresis. But here I think I was more trying to explore how the charge transfer happens, and how the current splitting affects the hysteresis. And that's why I didn't necessarily focus on trying to optimize the hysteresis or decrease it.
That might be something.
Something
someone
else
else
can
may
explore.
want to do.
Yes.
Oh, anyway, so, any other questions?
Yeah. Thanks for the nice talk. I learned a lot from it. Thanks for walking us through stuff. So my understanding, I guess, of your thesis a little bit is you're taking like this physics-based approach to understand the properties that would affect the performance, but that physics-based approach and what you learned here could, I mean, the big goal to improve our Grand Theft Auto 6 when that comes out, or 7, 2 decades or whatever. Yeah, it would be for the engineering side of things. And
Yes.
Mike's question about like the scatter in your data and I guess the variation in these devices, I guess. A bigger, I guess, down the line question I have is like, what's needed or what's the limitations here or challenges to actually get, that you wouldn't have to measure every single device, but you could get reproducible behavior with these type of transistors here.
I think the main thing would be finding a way of fabricating these in a scalable way. Let me see if I have this. Here we go. Okay, so. Right, so for large area integration, the main things we would need is synthesis and transfer. So we would have to, one, be able to reliably grow these materials in the thicknesses that we want. Second, we would want to be able to create patterns or a wide array of transistors to characterize all of them at the same time. So I think those two main areas are what's kind of stopping this from being at the forefront of our technology right now. And why it's kind of a slow progressing field. Because like I mentioned, it's very easy to just peel apart and create devices, but actually fabricating these in a very large area is proven to be challenging. So that I think that's the kind of bottleneck that we're at right now of trying to synthesize them in a larger controllable way.
And do you think the contact aspects are easy to address, or is that also an issue? Since a lot of your work was like what layer making the different contacts.
I think it's one way to tackle it. Like as mentioned here, there are many ways that we can try to optimize it. But definitely contacts, I think, is the easier way to do it, at least from my point of view.
All right, okay, I think we should move on to the second part of the defense.